Our next speaker is Haojing, who's going to tell us about the nature of very bright dropouts in JWST NIRCam bands.
Oh, it's all deleted, huh? I don't know what's going on. Okay, let me. There we go. Okay, that's proper. Sorry about that. Okay, so like I said, I'm going to talk about this very bright dropouts, and I'm going to talk about those in the context of very high redshift universe. Yuichi did a very good job this morning talking about very high Z universes, so I'm not going to go there again. But I would still like to remind people that the Galaxy redshift record now is pushed to Z of 14.32 by Jay's team recently, and I wouldn't be surprised if it goes even higher in the next few months. And I also wanted to add that I think I dare to say I was pretty much the only person who, before JWST's launch, the only firm believer that there ought to be lots of galaxies at a very high redshift beyond Z of 10 to 11. Now it's, the picture is getting clearer and clearer. And also, one thing that I also wanted to point out is that this very high redshift galaxy actually is a close neighbor by projection of a galaxy at the 3.47. All right. So the moral of the story is that you don't want to reject a legitimate candidate because of the projection proximity to a very local guy. Well, it's not a very local guy, but it's a low redshift guy, right? So yeah, so just, and also this is tied to one point that I'm going to stress today. And before I go to very bright, I wanted to talk for a little bit about bright, right? So about a year ago, we pushed this paper out, and we did a systematic search for very high redshift galaxies by this very classic dropout technique, using all the cycle 1 data. And we are still in the process of revising this paper. But in any case, the upshot is that there are a lot. And then there is this very, too bright and too many problems. Just basically, there are too many galaxies that are very bright at bright end. Okay, and this is just to show you the NIRCam bands, and we are starting from here. So we search for 150W dropout, 200W dropout, and 277W dropout. We didn't go there because, and then we'll be left with this classic problem of only one band of detection here, which makes things so uncertain. So we just search for this three dropouts in this 3 bands. And if you want to look at the redshift, it's very high. Okay, so if you really dare to think about that, 277W dropout, the redshift is somewhere around 24.7. I don't want to go that far, but it's just that if you keep an open mind, possibilities is there. And our tentative luminosity function that we put up here is like such. Okay, so there's a very prominent excess of the bright end. And from the recent theoretical works, for example, here we compare to this plus feedback-free burst scenario put forward by Deco et al. And Jojo this morning talked about this in detail. And there's a hope that this kind of new thought can explain the very bright end, although there's still some kind of problem here if you go to higher redshift. But in any case, this is not what I'm going to talk about today. What I'm going to talk about today is to go even brighter. Okay, go even brighter, and well, this is dangerous. This makes you popular because it's almost like a nonsense, but you have to stick your neck out, and this is what we are doing here. The thing is that in our earlier paper, we actually intentionally limited our sample selection to pretty faint end. Okay, so it's fainter than 26.0 Mach. Okay, for those three dropouts, 3 type of dropouts. And well, the only reason that we did that was because this corresponds to roughly absolute magnitude of -22, where you assume that AGN still is not a problem. Okay? However, there are lots of brighter dropouts. Okay, so if some of them are indeed at that kind of very high redshift, then we'll be in an even bigger trouble, right? So they have a quasar-like luminosity, and their stellar masses, regardless of whether you put in nebula emission, will be enormous. Really, really difficult to explain. And so this is why we wanted to understand them. They need to be understood so that our understanding of very high Z universe galaxy formation can be put onto a more solid footing. So this is what one of my graduate students, Thompson, and I have been working on, and we are at the final stage of wrapping up this paper. So I'm going to show you what we are doing here in this paper. So we wanted to select very bright dropouts in this in where we have mirrored observations. So we concentrate on Cosmos, UDS, and Sears, and also Good South. Okay, and if you look at now, we also extend to lower redshift. So we're also including 090W dropout and 115W dropout, and those are listed the nominal redshift range for those dropouts. And the break amplitude should be larger than 0.8 magnitude, and we require non-detection in the middle bands. The bands bluer to the bluer side of Lyman break. And so that's approximately about, well, we wanted to cut at brighter than -22 magnitude. So, and this is the brightness threshold that we adopt here. So those are very bright guys, okay? And in the old days, when you have limited passband in the dropout search for very high Z galaxies, you want to do color diagram diagnostics, right, to weed out those potential low Z interlopers. Today we have so many bands, so we can afford SED fitting. So we did SED fitting to screen out those potential interlopers. And we also incorporate HST ACS bands, and also, and like I said, more importantly, we wanted to have at least one band of mirrored coverage. So the common area between NIRCam and mirror coverage is about 200 square arc minutes, and there are about 114 objects that we selected in this four band dropouts. So this is a large number, right? But okay, let me show you these statistics about their brightness. So to make my point clear, so this is where -23 magnitude should be, right? At the four different redshift ranges. So if you go to brighter than -23, this is like, quasar-like. So the luminosity is going to be enormous. Now those are the image stamps. So this is 090W dropout, 115, 150, and 200. Okay, so you can look at their shapes. The common wisdom is that if you see something like this big and this regular, almost like a discs, they cannot be at very high redshift, right? But we also know that nowadays galaxies at disk galaxies up to redshift about 6, they are there. So let's keep an open mind. Just look at them for the sake of completeness. And also there are things that are quite compact. So most of those they fall onto these two categories: elongated and compact. Now, like I said, we need to do SED fitting to weed out those contaminants. So we use the 3 different tools. One is easy, and well, we use local templates. So the templates are from Brown et al. Back in 2014. Well, one of the reasons that we choose to use this set of templates is because we not have mirrored, right? So for low Z guys using a local template, presumably this is going to be optimized to find low Z solutions. And we also use the LaFar. This is kind of like a classic approach using BCO3 templates and tau model as the star formation history. And finally, we also use a Sigel, which is a pretty fancy tool. The underlying stellar population synthesis model is still BCO3, and we use a delayed tau model. And well, one of the reasons that we adopt this tool is because it has this functionality to adding AGN fraction. So we wanted to see whether AGN is going to play a significant role here. All right, so after this, we group those very bright dropouts by their photometric redshift, and we divide them into high Z, low Z, and undecided. And for high Z guys, at least the 2 tools need to give a good fit, where good fit is defined as you know, having raw chi-square less than 100, raw chi-square, not reduced one. And they need to consistently give photometric redshift larger than 6.4. And for low Z, well, same thing. At least the 2 tools give you know, good fits and also consistently Z of less than 6.4. And among high Z and low Z, we subdivide them into tier 1 and 2. For tier 1, you need to have all 3 tools give the same answer. And for tier 2, you know, it's otherwise. And also, of course, we have this one size fits all thing that's undecided. An object cannot be fit into either of these 2 categories. They are put into this undecided. So the sample statistics is like such. Although we hope that most of those will be low Z or undecided, and some of those they stubbornly, you know, appear in this high Z category, and also some of those are in this high Z tier 1 category. So this makes us really wonder what's going on. So I'm going to show you some example SAD analysis results like such. So these are low Z. So you know, this is DISCI guys is very well explained by low Z solution. Same thing here. This is a 090W dropout. This is a 115W dropout. Okay. So, and I can show you more. This is 150W dropout, and this is 200W dropout. They can all be explained really well by low Z templates. However, like I said, we do have high Z template, high Z solutions here. Okay? This is a tier 1. We have 7 of those, and tier 2 have about 8. And if we look at their SCD, it's like such. Okay, and this guy is like this. Okay, so it's this key shape, and also this one. And I can show you more. This one is pretty close to what people would call little red dots nowadays. Okay, so this is a little red dots, and this one here is a bigger red dots. But in any case, those are, you know, high Z tier 1 guys. Now we do have some very limited spectroscopic identification that we can get from the existing data. So in this work, we used pretty much all of those, and we found that some of those are covered by these 5 programs I listed here. Let's go ahead. All right, and as it turned out, 7 of them were observed by this the program listed here, and are all in prism mode. So spectral resolution power is something like about 32,300, or give or take 100. And they are all at redshift of 3 to 4-ish, including some of those at the tier 1 high Z. I'm going to show you some spectra. And so we rank them for the Z spec. We ranked their grades as A, B, and C. A, you have to have at least 2 lines giving the, you know, a very solid redshift. And for B, only 1 mission line, but we can sort of guess based on photo Z's. And for C, there's no feature at all for us to identify. And also, I wanted to point out this guy. Okay, so this is a tier 1 guy, and the spec Z is at 3.46. So, you know, at least we have 1 extreme case removed. Well, this is just to show you a grade 1. Okay, so you can see that this guy and also its neighbor now at a redshift about 3. So this, you know, multiple lines. So the redshift is very solid. And this is grade B. You have only 1 prominent line tentatively, there might be an O3 line here, so we put a question mark here. There's at least a one line for us to say something. And also we have this grade C. You have no obvious features to identify redshift. Yeah, just to show you this three grades. And now this one, I want to spend a few seconds talking about this guy. This one is what we call tier 1, right? But based on photo Z's. And for here, you can see that we have 3 emission lines, and the redshift is a 3.46. Okay, so SCD fitting previously, we have SCD fitting like such, very consistent, very reasonable fit. And if we fix our redshift to spec Z's, and this is what we get. And you can see that a chi-square, let me flip it back and forth here. So this is, say like, here, you can see that the chi-square here, for high Z solutions, chi-square is pretty small, but for this low Z solution, fixing at the Z spec is very high. Right? So it's just that for the metric redshift, regardless of how popular they are, well, they should be, they can go very wrong. Yeah, so this is what I wanted to show. And I could end my talk here by saying that, well, they are very bright NIRCam dropouts, and some of those are, as bright as about 23 magnitude in 356 W, and or correspond to minus 24 magnitude if they are at very high redshift, right? And if a significant fraction of them are indeed at that kind of very high redshift, we will have a very big problem, even bigger problem than we are conceiving today. And those objects are not exactly like those little red dots or what people nowadays call HST dark galaxies. They are related, but they are not exactly the same. So we really need some more study on those. And although, like I show you, the existing spectroscopic data, at least we moved one out, one very extreme case out. It really doesn't mean that the concern is gone. We still need further JWST spectroscopy. So if any of you have some program, you have free slip, let me know. I can provide you a list of our target as fillers. I'll stop here and take questions. Thank you.
Thanks for that. We have a couple minutes for questions. I'll kick it off. Oh, you want me to?
For the object that you showed with H alpha, I noticed that the other 2 lines were sulfur 3 and helium 1, I believe. Yeah. Is that a reasonable looking spectrum for a galaxy at that redshift and those properties? I mean, do you see, can you produce that with
the thing is that, yeah, the thing is that, well, the derived redshifts matched exactly. No, we cannot. We cannot. Yeah, so, but this is a totally separate story. Yeah.
I think one of the surprising things for me about these candidates is they're basically all spatially resolved, right?
That's right. That's right.
You don't really expect that at redshifts of 17 and above.
That's true.
But it does give you the opportunity to do spatially resolved fitting for the redshifts, and you can check whether or not the pixels on the inside of the galaxy give you the same redshift solution as the pixels towards the outside of the galaxy. So if you thought about doing this?
Yeah, we are thinking about doing this, but not at that kind of, well, not, for those objects, they are still a little bit too small to do this kind of thing, because when you try to do PSF match across the bands, things like, they are smeared out. So it's not that easy. We are doing this kind of a, spatially resolved SCD analysis at much lower redshift when things are.
Any other questions? If not, let's thank our speaker.